Okay, so square planar crystal fields. This is the one where my drawing doesn't do the best. Okay. All right, so let's start. Oh, we'll try to look at the dx squared minus y squared. We're going to try and figure out which ones of these go higher in energy and which ones go lower in energy. Okay, so this is the point where everyone's going to go, did you ever take an art class? I did. I just had it. Actually, instead of drawing this, let's put the metal right in the center so we know what we're working with. So there's our metal. Find the z-axis there.
Are the lengths of your axes on purpose because it's square planar?
Yeah, I made those longer just because I'm trying to give myself room to draw things. So what we're going to have is first we are going to have two of the lobes going that way. And two of them along the x-axis. Now, we want to imagine our ligands as point charges coming in. What I want to do is draw them like this. So you get a sense of the phase of the ligand field. So you see, we're going to have two bonding interactions, but we're going to have two head-on antibonding interactions. That's going to destabilize and drive it way up in energy. Okay. So next, I want to look at the dxy. Oh, this is where it starts to get bad. Okay. Now this one is going to lie. That's horrible. In the xy plane, between the axes, see, that always makes it look like it's going up the z-axis, but it's not. And then we'll have our ligands coming in. So you're going to get bonding, antibonding at the same time as the ligands come in. So you get A little less destabilization than the head-on interaction antibonding. Now let's take a look at the DZ squared. We're going to get it all looking like that. And then now, believe it or not, you're actually going to get quite a bit of interaction. You're going to get quite a bit of interaction with that little bit of the antibonding ring in the middle. But you see how we're getting less antibonding energy with that middle ring than we are with the full-on orbital lobes of the previous two. And then you have your DXZ and DYZ, which I'm only going to draw one of these because you'll get the idea. And for this one, I'm not even going to draw the x-axis. I'm just going to draw Y and Z. Move our metal in the center. Yeah, I guess I could have drawn. Yeah, I'll put it in there. Because of course we still have the ligands attacking in the square planar. Okay, so what we're going to have then is the ligands are attacking, so especially at this front and back, they're not even attacking in a direction where there's orbitals sticking out. Okay, the two on the sides are kind of hitting like in the middle there, but those two coming in along the x and negative x direction, they're not really having too much interaction at all, which is going to it will end up allowing minimal interaction with the antibonding, and it will allow a little bit of interaction with the orbitals of the same phase. So these are going to go lower in energy. So once you get this all done, you go back up and you go, okay, which one is which? How do I put these in order? Well, based off the configuration, you're going to have your lowest energy is your DXZ, DYZ. That's where you have ligands hitting the orbitals on the front, like on the front and back plane. Your next one is going to be your DZ squared, then your DXY, and finally where you have the head interaction, DX squared minus Y squared. And so when you look at these, you want to kind of ask yourself, like, how can I rationalize that some of these go up in energy, some of them go down in energy, so on and so forth. Because again, like your DXY, you see how it actually stabilizes a little bit from the octahedral field, because you are getting you are getting some bonding interactions. You're getting some anti-bonding interactions, which is not nearly as severe as it is for DZ squared. But it's going to be a little bit higher in energy than DZ squared. And then, well, the energy separation we're worried about, that's your square planar delta right there. Square planar complexes are very likely to be low spin, which in this case is going to incorporate this level, and this level. Okay, that delta SP is usually quite large, so you're very rarely going to get electrons up here. This is what's going to happen when you start getting to your 4D and 5D metals. They're going to become square planar complexes. Okay, let's look here. We have nickel chloride. I should have looked up the. Well, I didn't write down the name. Anyway, your PPH3. I mean, it's a triphenol. You can see that. But your PPH3. This is a very common ligand. And again, in textbooks, you always see it as an abbreviation, but this is what it actually looks like. So the first thing you're going to notice about that, what kind of interaction is this going to have that, well, let's see. So it's going to have a kind of interaction that's going to negate an octahedral complex. Right off the bat, what do you think that's going to be? What kind of interaction is going to negate an octahedral configuration? Imagine putting 6 of those in a ligand field.
Steric hindrance?
Yeah, you're going to get tons of steric hindrance. This is a bulky ligand.
Sure.
So you're going to be reduced to a tetrahedral or a square planar. Okay, so let's take a look at the nickel chloride. So first off, what is the charge of nickel in that one?
Let's see. Is it gonna be 2?
Mm-hmm. The PPH3 is neutral. You have 2 chlorides, which means that nickel will be a 2 plus. And when you check this out on the periodic table, it's going to be a D8 complex. Okay, so you also know that this is paramagnetic. Okay, so based off the hindrance, it's going to be pushed into a tetrahedral configuration. And I also know that the fact that it's paramagnetic also tells me that it has to be tetrahedral.
Why?
Because let's go back up to here. Here. Look here. You're not going to cross that delta SP. So if I put 8 electrons in there, do I have any unpaired electrons?
No.
No, so that would be a paramagnetic.
Okay.
And so this is diamagnetic, so I know I have that bulky ligand, diamagnetic, and it is it's a 3D metal. So it's more likely to go, the 3D metals are more likely to go octahedral or tetrahedral. And so it's like, okay, well, everything's pointing to the tetrahedral. So let's look at that configuration, our tetrahedral. You know, our T2 level, our EG level. And then we have a D8. So 1, 2, 3, 4, 5, 6, 7, 8. Now, one thing that's problematic here that you might get confused on is this is a strong field ligand. So based off the fact that that's a 3D metal, and this is a strong field ligand, what might your first guess be at orbital structure?
At orbital structure.
Yeah, so what kind of field would you guess based on the strong field, this being a strong field ligand? My arrows are horrible, aren't they? Strong field ligands are going to tend to want to go, well, they're going to tend to want to go low spin, but you might guess octahedral based off this being a 3D metal. And so here, again, you have this kind of ligand where you're on the border where your steric effects and your ligand competition are going to counteract the strong field nature, but they're going to compete with the strong field nature of the ligand. And so since they're competing, and you have two of those, but then also, it can't, real simple, it can't be an octahedral
There's
line.
not 6 ligands.
Yeah, there's not 6 ligands.
Okay.
So maybe I should point that out to start with. But but then your chloride is a weak field ligand. And so because chloride is a weak field ligand, now the strong field ligand really suggests that you want to push these levels apart. Your strong field ligand is going to then counteract that and bring the T2 and the EG back together. And so everything is pointing towards this tetrahedral configuration. Let's just forget the fact that there's only 4 ligands to start with.
Okay.
Let's kind of think about this in terms of, because there very easily could have been PPH4.
Sure.
But we didn't get there because that's just too much interference. Even with the chloride, there's still going to be too much steric interference to really go up to the octahedral configuration.
Okay. But you're judging that a lot off of it being like paramagnetic.
Mm-hmm.
So that yeah. Okay.
Now, I mean, you can make the arguments of the chloride being a weak field and the PPH3 being strong field, and would this be a high spin or low spin? But it's a D8 complex, so it doesn't matter what. Like if it was a D4, we could really argue that out.
Sure.
But it's a D8, so we have to have those electrons go somewhere, so they have to go into the T2 level.
Right. Okay.
Okay, so let's look at the palladium complex. So palladium is a 2 plus. This one is also going to be a D8 complex, but when you look at it on the periodic table, you now have krypton, four D8. So this is a 4D, it's a 4D metal. So we're getting bigger.
And because it's diamagnetic, it's more likely to be the square planar.
Yeah, remember, this is a much bigger ion. This is a much bigger metal. And so you are going to eliminate a lot of your steric effects with the larger metal. However, the larger metal with the much more diffuse orbitals is going to push you out into a square planar complex versus an octahedral.
Okay.
Okay, so what does this tell us about the electronic structure? We know it's diamagnetic, it's D8. Well, if I draw my square planar field, so no, it's XZ, YZ. TZ squared, DXY, DX squared minus Y squared. Okay, and so then D8, 1, 2, 3, 4, 6, 7, 8. Okay, so that matches the paramagnetic. We could test this. We could say, well, I know it's a 4D metal. Man, it's really not gonna. I know it's really not gonna reach that octahedral configuration. But even if I had octahedral, there's my octahedral, and if I did the D8, and let's say you're competing, chloride is a weak field, PPH3 is a strong field, so your delta O is going to be, not as small as it could. Not as small as it could be with the weak field, not as large as it could be with the strong field, but we have a D8. So let's see, let's do 1, 2, 3, 4, 5, 6, 7, 8. Well, that does not match diamagnetic. What about the tetrahedral field? Okay, that doesn't match either. So it just can't be either one of those. This metal is going to have to be in a square planar configuration.
Okay.
So we are kind of into a part of this where there's not as much math, but you're really having to work with this conceptual. And you're saying, oh, okay, well, what is the data telling me? And again, you test this in a lab, you're like, oh, this is a diamagnetic molecule. Well, that's going to tell me about its ligand field structure.
Yeah.
So again, a lot of this stuff that you're getting here is not so much mathematical workup as it is, this is what you get in experiment. What is it telling you?
Sure.
Which is more, I think, you're good at the math and you enjoy it, but I think you enjoy being in the lab more.
Yeah, probably.
Okay, so let's look at some D3 octahedral complexes. What's W?
Tungsten?
Tungsten. Tungsten 3 and chromium 3, both with nitrogen donor ligands. Because I wanted these to pretty much be very similar. So let's see. And I forgot to put the rows of the periodic table. I forgot. Anyway, well, chromium, I know chromium's a 3D. Well, I think tungsten's a 4D. I really wanted to look at the differences between these two fields. And so we're looking at, again, UV vis data, okay? You get photon absorptions at different wavelengths. If we look at the wavelength at the top of each, so again, you remember that equation with your lambda max?
Yeah.
So if you were doing a UV vis experiment, do you know which absorption would be your lambda max?
Which absorption would be? It would be the. Wait, which absorption would be the lambda max?
Yeah.
Would it not be the top one, the biggest?
It's going to be your lowest energy.
The lowest energy. So that 0.086 one?
Yeah, so well, you're going to see these absorptions at different wave numbers. Your lowest energy wave number technically represents your lambda max.
Because it's an inverse?
Yeah. So I wanted to look at some of these and see what we could see if we could tell the delta O for each of them. Because again, here you see everything is still measured in turn. Now I call it delta square planar, but most of the time, all of these are still calculated as delta O's. Okay.
I don't mind paper notes from the other day.
So if we look at the chromium 3 complex, so we have our hc over lambda. But h is your Planck's constant, c is the speed of light, and lambda is going to be your 465 nanometers. You end up getting delta O 4.27 times 10 to the negative 19th joules. And for your tungsten, so you're gonna see a massive difference in these energies. And so this is indicating to you that one of them is more tends towards an octahedral field, and the other one tends more towards a square planar field.
Oh, okay.
Okay, so again, your delta O using this time the 450. It's going to give you 4.42 times 10 to the negative 19 joules. Now, so this is in joules. Looking at those, do those look like a massive difference?
Not particularly.
Okay, well, let's put this into, so the difference between the two, this is going to look weird. The delta O, that looks weird, but you know what I'm saying?
Yeah.
Is 0.15 joules. Okay. Well, that much, a whole bunch. Let's put this in terms that biochemists, organic chemists, biologists would understand. That is a difference of 2.16 times 10 to the 19th
Calories.
kilocalories per mole, which is an obscene number. It's also a difference of 9.4 times 10 to the 17th electron volts. So you can see that delta O for the larger tungsten is huge.
Right.
So that means you're not going to get any electrons that are crossing that. You're not going to, you're really not going to get that high spin configuration. You could make arguments for tungsten being in an octahedral field, but the delta O is just too large to warrant that.
Mm-hmm. Large for octahedral.
Mm-hmm. Your tungsten with that large of a delta O is going to lead to a low spin environment. And when you start getting things, so like try to do anything past a D6, beyond a D6 for tungsten, well, I mean, in the 45D metals with a delta O that large and make it octahedral. Try to do anything with a delta O that large. I mean, so are there square planars where you could technically get things up in the dx squared minus y squared? Yeah, but you're going to have a lot more room for your low spins for most of your metals in the 545D regime and the square planar regime. Because again, even your tetrahedral, if the delta O is that large, you're kind of like you get kind of stuck at that D4 stage. It's just when you see delta O's this large, you're going to go you start to think, okay, this is more than likely going to be a square planar. Might be one of the others, which in your book they didn't have a table of the orbital configurations for several different types of ligand fields. We've just looked at octahedral, tetrahedral, and square planar. There are others like a trigonal, bipyramidal.
Sure.
Just so they have them there. And it gives you an idea of energies that you're looking for that are going to specify these large in this square planar configuration. Yeah, in joules it doesn't look that big, but in kilocalories per mole, you can see, oh yeah, that's huge. Oh, look, I have words here. So again, you're limiting steric effects, so you're not being pushed. So those steric effects are really what push your 3D metals into that tetrahedral regime. They want to be octahedral, but they just can't with the ligands that they have. Then the huge delta O, you lead to low spin environments, which then pushes you towards that square planar configuration. So as you go along, like if you did something with this in graduate school, you'd go much more in depth with it. But just for now, you want to be able to look and go, oh, that's a 45D metal. I'm probably going to have a square planar ligand field.
Yeah, I can tell we're only scratching the surface. It's like clearly a lot is going on.
Well, just a topic like this, just ligand field theory, you could make a whole career out of experimenting with this.
Sure.
Just trying to figure out what's going on. And so like with the molecular orbital theory for octahedral complexes, again, this is all approximations, but because in reality, these are going to come together and form their own unique set of wave functions. But for this one, the one I wanted to look at, or the one we're going to start with, is a low spin complex. Mhm. Okay, so it's going to be cobalt 3. which becomes a D6 complex, or is a D6 complex. And then let's think about, so again, it's very clearly octahedral.
They're
And,
the opposite of the number of ligands.
yep. And it's going to be low spin. It's low spin. And so what tells you that that's going to be a low spin complex?
The ligands.
Yeah, what kind of ligand is it?
Low, yeah, low spin.
So it's going to have pi back, but well, will this one have pi back? Yeah, it will. I think. No, actually, it won't. This one won't. Okay, so what tells you that this is going to be a low spin environment?
It's the kind of ligand that it
Yeah,
has.
it's a strong field ligand.
Strong field ligand.
Mhm.
That's what.
Okay, so now this is where we start to deviate a little bit from Gen Chem. The normally in cobalt you would say, well, the valence is going to be the 4s and 4p, but we actually get d electrons that are going to behave. Some of them will behave as valence. Sometimes they will. Sometimes they won't. So we have to take account of the whole shell. Give us our 3d, 4s, and 4p electrons. Your 4s orbitals, if you go back and look at these, it's going to be A1G in symmetry. Your 4p orbitals are going to be T1U in symmetry. Now, of course, the 4s and 4p are empty as of right now, based on the fact that this is cobalt-3, but they're still available quantum mechanically, so we have to account for them when we're looking at the ligand field. Okay, and then of course from the otherwise you get the EG and the T2G orbitals. So let's kind of take a look at what all these might look like. So there is kind of a regime for drawing these. Okay, so we're just going to have this sphere right in the middle for our 4s. Okay, this is also our A1G. And so the way what this is going to become and this is why, so this, we're using ideas of hybridization here to try and explain what's going on. So what we're going to get is that's going to split into an orbital system that looks that way. That are now, they've kind of split and they're reaching out into space waiting for a bond. Which now I'm wondering if I gave myself enough space. We'll try. Okay, so your 4p, it's going to be your T1U, so you have 3 of those. So this one, we're just going to remember that we start with a p orbital, but we end up with bonding orbitals that kind of stretch out like that. And then we get that for each one of the p orbitals. So let's see, then we'll have our y orbitals. And our z orbitals. Those are kind of sitting there waiting. Let's take a look at our EG orbitals. And what is this? So this one is our T1U. And this just went from there to there, just kind of showing how the p orbital will then hybridize into this bonding orbital system. So now we're going to do our look at our EG orbitals. And when we're bonding, these will be kind of problematic, which is going to explain their energy levels. Okay, so the first one. So if we look, our EG. So we know you can look back in your slides. You know that that's dx squared minus y squared and dz squared for the octahedral field. So from the dx squared minus y squared, I'm going to use a system like this. And from our dz squared, okay, so up and down, we get that fit. No, you get that phase. And then due to that little donut in the center, and this is from your dz squared. So you can kind of think of the way that orbital looks, and then that this branching out makes starts to make sense. And these are our EG symmetry, and then we'll take a look at our T2D symmetry, and then we'll take a look at the ligand field orbitals.
So, okay, what exactly is the reason that they're getting all spread out?
Because we want to make bonding orbitals.
Mm.
So your bonding orbitals are going to actually be wave functions that are more they're going to be more diffuse. And so this is just a regime for drawing them that shows that these are no longer like the P or D orbitals we're used to, that they've mutated into something different. And they're so you see there when we go from here to here, you notice how we went from a common p orbital to something that has the same phases, but it's now just kind of it's denoted as something different that we now know as bonding orbitals. And so then our T2Gs are going to go from our dyz dx dxy. Okay, so from our dxy, actually dyz. That's going to give us, these are so hard to draw. Now let's do the dxz. I think it's easier to see if we only draw two of the axes. Man, this is hard to draw. Um, so something kind of like that. And something kind of like that. Yeah, not good, not good, but. And then our dxy. Alrighty. Well, something kind of like that. And these are our, that's T, X, Y, and these are our T2G. Or so these are all the orbitals that are made for bonding by the metal center. So then we're going to start thinking about the ligands. So, and we also want to think about where electrons come from. Okay, so there's going to be 18 total electrons ready for bonding. 12 of them are going to come from the ligands. So of course you remember these form coordinate bonds. So the ammonia are going to donate 2 electrons apiece, and there's 6 of them. So that's 12 electrons just from the ligands. Okay, now the way these look. Well, I'll do a few of them. Just to kind of give you an idea. Now we're almost out of time. Let me at least show you the A1G so you can understand where we're going with these. I wanted to take the time to do these because your book gave a reference to some table somewhere. And I was like, well, let's actually try to make sense of that. So we were XYZ. And then I drew that one backwards. Okay, so we're going to have is the your ligands are going to come in with these p orbitals or kind of hybrid orbitals, but still basically p orbitals. Because even though we're not going to do every single combination, I want you to see again, we're back into a regime where only orbitals of specific symmetries can bond. And then we need one along here. So this is going to be our A1G ligand field. And you'll see later on, because we're going to match it up with the A1G up here, you can see how that's going to line up. So there's your A1G there. And there's your A1G there. You can see those are going to line up pretty nice. So again, we're only going to do a few of these, so we'll finish this on Wednesday and keep moving forward. But try to make sense out of some of these shapes and their symmetries, so you can get an idea of what we're looking at here.
Hold on, let me there's a Friday I'm gonna miss. Isis